Hello and welcome to the lecture Optimizing CNN Part 3. In this lecture, we are going to discuss the definition of the dropout and then how dropout to resist the overfitting. Then we will discuss weight sharing, data augmentation and training and hyperparameter tuning. So, we are discussing about the problems of deep neural networks. Now, in this lecture, we are trying to understand the problem of deeper networks in context of overfitting. Now, as we know, what do we mean by deep nets? That is a many nonlinear hidden layers between input and output, which making them very much expressive to learn complicated relations or a very complicated patterns. And this mapping, this complicated relationship or mappings between inputs and outputs. Now, if a model is very deep, it can learn complicated relationship fine, but at the same time, this model, high model complexity, makes the deep learning network to memorize intimate details, especially if a situation is like this, the model complexity is very high, but training set is not that much big. So it starts memorizing the intimate details of training set. And sometimes this training, some points is in the training is maybe outlier or noise, but it's also learn this. This particular tendency of the model makes lose the generalization. And this causes overfitting because it downgrades the testing accuracy substantially. So, in our previous discussion, there is a different kind of methods to reduce the overfitting. Maybe cross validation, early stopping, this L1, L2 regularization, weight sharing. In this lecture, we are going to introduce another very interesting concept which is called dropout. Now, let's see what we mean by dropout. Now, as we understand, the best way to regularize a fixed size model to get an average prediction from all possible settings of the parameters and aggregate the final output. This is basically a Bayesian approach. Theoretically very sound, but it is very computationally expensive and almost infeasible in real time. So we cannot do the inference or prediction in real time by this approach. Also, it's a theoretically very sound approach. So what is the other way? We can train many models on the different bootstrap samples or bootstrap samples of the data and average their prediction to reduce the variance and improve generalization. This is another kind of ensemble or bagging kind of approach. But again, this requires multiple models to be trained and stored. And in our modern time, recent times, that this become a huge challenge as the network become very, very big or very, very deeper. So with this background, dropout can be viewed as an approximation to bagging approach, a kind of ensemble approach. Bagging means bootstrap aggregating. but it done inside a single neural network instead of training many separate models. So we don't to train and store the many models. Rather, in a big model, in a single big model, we create some instance of subnetworks and do this ensemble method within. In other words, dropout is a regularization technique. It's used for neural networks to prevent overfitting by randomly turning off or dropping some neurons during training. So that we are going to understand. Let's see. So what happens in dropout? So during training time, that neuron is randomly deactivated. You can see this neuron is deactivated. This neuron is deactivated. This neuron is deactivated, and so on. So this deactivated means what? It don't contribute in the forward pass or don't involve in the forward pass, and it's not being updated during the application. The question comes, how many such neurons being deactivated? In general, it is the probability is 0.5. It may be different, but in general it's 0.5. But testing time, what is? No such neurons are dropped, but their output is taken, scale version of the actual output, and this scale is P. So the full network is used, only the scale version of output is taken. Now, dropout can be thought as a bagging method. Why? First, we have to understand what the bagging is doing. So, many models are trained on different bootstrap samples of data, and this average of predictions are taken to reduce the variance. That is a simple way of bagging. There is a different models, given a data, we train the models and average out the inference. That is a simple techniques or very simplistic definition or understanding. But this essentially reduce the variance. What do you mean by reduce the variance? It means it improve the generalization, as we know from our the concept of bias variance. Now, what we doing in dropout that essentially resembles bagging? During training, we drop the neurons randomly at steps. So we get different subnetwork, and these subnetworks are being trained during each mini batch or in set of training examples. And such subnetworks or ensembles of exponentially many subnetworks that all share weights are implicitly being trained at the training time. So this ensemble of a group of this exponentially many subnetwork is being trained, but weights are shared at the training time. And at test time, what we are doing? The full network with scaled weights are used, and this approximate the average prediction, approximate averaging of predictions. This is important, average prediction from all these subnetworks. So it kind of bagging techniques, and it also helps to reduce overfitting. Now, what then dropout is, in a very naive understanding, dropout trains an ensemble of all subnetworks. Subnetworks formed by removing non-outputs units from a underlying base network. So this is the network, and we have seen we just deactivated some of them randomly with a probability p, and p is 0.5. we can effectively remove units by multiplying its output value by 0. But essentially this, what do you mean by neuron? It's input to output mapping. This is a kind of performing a series of affine transformation or kind of and putting some nonlinearities. And this is big. We are now randomly on and off the neurons in case of dropout. So here we can say how this ensemble are being created. This is just very hypothetical scenario. This everywhere is this is the non this is the output. So apart from this output is 4 neurons. So 16 such combination. Sometimes there is no cut, is not required also. One important thing to understand here, that all subnetworks are not required to train because it is only 4. Now you can say if it is a 40, then you understand 2 to the power 40 is a huge, then it is practically infeasible. But is it required to train all the subnetworks? No, because only it is required to train all the parameters. And you can say here this and this all H1 H2 are being trained. So many times it is being learned. It is not required to do this. Before that, train all our parameters. Okay. So at training time, what we are doing? At the training instance, then in particular mini batch, an instance of subnetwork is formed by randomly removed a set of neurons. In general probability P 0.5 from non-output layers. And a different subnetwork in a different training instance. Weights are shared across all the networks. And during training instance, parameters of existing neurons are involved in forward pass and getting updated during backpropagation. That will also. This is we done in the training time. Similarly, in the second instance, the first instance, these and these neurons are deactivated. In second instance, these neurons are deactivated. Other set. So another instance of subnetwork is used to get another subnetwork. So this set of here also, this set of weights are being involved in forward pass and getting updated. And deactivated neurons are not involved. And these training instances are continued, and essentially when all parameters are updated in such a way, we can get this intended input output. Okay. Now what happened in the testing time? The full networking being used. So all that, but it is scaled, output is scaled, because we have to understand this particular neuron is being used with probability 0.5. So its output is just scaled with this 0.5. Every time it is being used. At a training time, this is used, but it is used with probability 0.5. But testing time it is used, but their output is scaled by this fraction. So it is done in the testing time. Now the major question comes, how this dropout helps to reduce overfitting. Okay. So dropout makes it hard for network to rely on a single feature of neuron. What does this mean? This is very important statement. That what dropout makes, that it makes to network to understand or realize or to rely not on a single feature or a single neuron. That a single feature is learned by a multiple neuron. or multiple neurons. Multiple features are basically distributed over different neurons. By enforcing neurons to learn, the features to remain useful even when their neighbors disappears. So this is very interesting, that we'll see. They create this kind of analogy. This helps to prevent overfitting, and we have to understand how. First up, to understand when overfitting happens. Overfitting happens when the neurons co-adapt. That they learn noisy patterns that only work when specific other neurons are present. Okay. And dropout breaks this co-adaptation by turning the neurons off during training. That we have to understand. What do we mean by co-adaptation? How it means trained. It's basically dropout breaks this. So the network is forced to learn redundant, robust representation that work in many different contexts. Now first we try to understand what do we mean by co-adaptation. So co-adaptation means the neuron X co-adapts with neuron Y, realize that Y is there for helping. So if there is no dropout, these neurons learn in that way. There is always some Y at our neighbor that will going to help us. So this pair over specialize, it's reduced generalization. But the dropout makes the learn feature remain useful when their neighbor disappears. So dropout breaks this co-adaptation, making the neuron X to realize there is nobody to helping, nobody for helping, nobody is come for your help. So you should learn the feature that works on its own, and feature becomes more general and transferable. This kind of learning makes the generalization higher, and this is the concept of co-adaptation, or better to say how overfits breaks the co-adaptation to reduce the overfitting. Now, another important thing is implicit ensemble averaging. That what dropouts is basically doing, that it averages the outputs for this a group of subnetworks. Each training step samples a different subnetwork, and these millions of subnetworks are being trained. And testing time, what we are doing in full net, averaging a scaled version of it. This averaging reduces the variance. And what do we mean by reduce the variance? This means it reduces the overfitting. So in this way, the ensemble averaging, it's basically reducing the overfitting by reducing the variance. And it also limits the effective model capacity. What is effective model capacity? It's basically the model complexity. Even when the architecture is large, what we are doing, we are basically remove or just chopped off some neurons, which make the resultant network is thin and subnetwork. So the effective model capacity during training is smaller, which is good enough to learn, but not that much high or that much large to memorize. And that is the very much effective for reducing overfitting. And it also encourages the feature redundancy. The important information must be encoded across multiple neurons. So not only one neurons it model it, rather multiple neurons. It prevents neurons to be memorization. Rather, it make it generalized. So this redundancy improves the generalization and increase the testing accuracy. That's definitely reduce the overfitting. So in this way, we can understand how dropout basically helps to reduce the overfitting. Now we are going to understand how weight sharing helps in improving the convolution neural network. So what do we mean by weight sharing? That weight sharing in CNN uses the same filter kernel with the same set of weights across different spatial locations of an image. So that we will see in a example that how it works. Now it lowers the computational complexity by substantially reducing the parameters because these weights are being shared, and it also somewhat helping to reduce the overfitting by enabling the translation invariance, recognizing patterns regardless of the location, by efficiently detecting local features like age and texture everywhere. Because the kind of similar filter or convolution kernel are being used because of this weight sharing. Rather than learning a unique detector for every location, the network learns one shared detector by sharing the weights and reuse it across the input, making the model smaller, faster, and more robust to the object translation. And this is called translation invariance. So what we have seen weight sharing, that rather learning a particular detector with different weights, we can use the filter kernel with shared weights and it reuse in different position. It makes the model smaller, faster, and more robust the translation. Now here we can understand how it works. So basically what we do, it is a fully connected layer, so neurons are connected. But here local connectivity, you can see these are the different two words, different kernels. Okay. And here we can say if the two network are the same weight, same, we are different. So the same kernel here. This is called weight sharing. Okay. So generally what we'll do, we'll slide the filter as we slide, you can see here in this position, image patches, a small filter, maybe 3x3 or 5x5. It slides, that it convolves across the entire image with this CRD weights. The numerical values are within the filter remain identical at its most position, and we get the corresponding feature maps. The output is feature maps highlighting where the specific feature image appears in the image. So this is called the weight sharing. How it benefits? It parameters, basically this parameter efficiency. So definitely it is, since weights are shared, drastically lowered down the parameters or learn. So fewer parameters to learn compared to the fully connected network, and that substantially reduce the memory and training time. It makes a translation invariance or equivariance because detects the feature regardless of where they are in the image. So its eyes and eye where the corner or the center. And it's also help regularization. Next of the regularization, reducing the model complexity and example. And it learns local fit pattern wells, forces the network to learn meaningful local patterns, edges, corners that are useful everywhere. So it's building the spatial hierarchies for that. So in this way, the weight sharing helps. Now our next agenda is data augmentation. So what is critically we understand in our convolution network, if network is very big and model complexity is very high, and under the supervised paradigm, this supervised training samples or annotated training samples are very much costly. So there is a frequent case that the not enough training data is available for train a very big network. In this situation, data augmentation helps. So data augmentation is a critical technique used to convolution neural networks to artificially increase the size and diversity of the training dataset by creating a modified version of the existing image, by rotating, by flipping, etc. This process helps CNN models to improve generalization, reduce overfitting, and enhance robustness to real-world variations such as lighting, position, orientation. So what it makes that what we understand here, that in our supervised learning scenario, where large number of annotated data is expensive to get, or there is a certain data scarcity, then this a given image is somewhat modified to get some new data samples, and it essentially improves the generalization and reduces and enhance robustness to the real world variation kind of thing. So at what we have said, that is mitigate the data scarcity. Supervised deep learning model specially CNNs require large amount level data. Well, data augmentation provide efficient way to expand data set when obtaining new and volatile consumer expense. So that what we exactly said before, that in real world situation, that this getting this annotated data is expensive and time consuming. So we can the kind of modified images or kind of input data to get large amount labeled data. Now it reduces overfitting by exposing the model to slightly altered images. It is prevent from memorizing specific features of the original training samples. This acts like regularization, forcing the model to learn more general invariant features. But we understand one thing, that if the data number of data samples are less, essentially for a bigger network, then there is a chance of overfitting increase. So by this data augmentation, if we increase the number of input data in supervised case, this is annotated data, then definitely this chance of overfitting becomes less, and which essentially improve the model robustness. The artificially generated variation, easy changes, rotation, and lighting, helps the model recognize objects under the variation condition it might encounter in real world scenario. Because when we change these conditions and different lighting conditions or different deformating, that it has the different cases of input modalities or this input viewpoints, or there is a lot of kind of way to represent a particular input that we can see here. So geometric transformation we can, rotation, translation, scaling, cropping kind of show this, and photometric color space transformation, brightness control, contrast, saturation, hue, shape, grayscale, making grayscale, such and such. So GAN-based techniques also being synthetic image generation. So that is a different issue, but data augmentation is basically like this. So that will help us very for reducing overfitting. Our next and final agenda of this lecture is training and hyperparameter tuning. Here we have to understand how CNN or training of the CNNs involves optimizing architectural learning parameters. What are the learning parameters or architectural parameters? Learning rate, batch size, dropout rates, filter size, etc. And choosing it judicially, it will help to maximize the accuracy of the data or testing accuracy. So key strategies include efficient optimizer like Adam, that employing the learning rate scheduling and utilizing techniques like dropout to prevent overfitting. Okay. Other key hyperparameters are learning rate. It determines how to step size during learning. That you all know what is learning rate. A rate too high to cause instability, too slow to cause slow convergence. Batch size. In a mini batch, how many training samples we are going to take. So number of training samples reduces one iteration. Smaller batch, better generalization, but larger one speed up the training. So there is a trade-off that we have to make this choice judicially. That which optimizer we can algorithm like this stochastic gradient descent, RMS prop, Adam is often preferred as for the faster convergence. So choosing optimizer is another thing. Dropout rate. Generally we use 0.2 to 0.5. We very frequently use 0.5 to prevent the overfitting by randomly setting to 0. Architectural setting, number of convolution layers, filtered, kernel size, and stride, etc. These are the key hyperparameters for getting to improve the performance of the CNN. So in this lecture, what we have discussed, we first define dropout and then try to understand how dropout to reduce overfitting. Then we discussed briefly weight sharing, data augmentation, and training and hyperparameter tuning. In next lecture, we'll discuss about how residual connection is being used to handle the vanishing gradient problem. Thank you very much.